Hey guys, welcome to my YouTube channel, Bite Size Concepts. And as promised, today I'll be explaining ionic and covalent bonds to you, in a bite-sized manner of course. So let's get into it. First things first, you need to know a very simple concept to understand ionic bonding, that is electronegativity. So electronegativity is basically the tendency of an atom to attract electrons towards itself. Basically, as you can understand from the definition, electronegativity increases with an increase in the number of protons in the nucleus of the atom, or it depends on the nuclear charge of the atom. So, let's proceed. So, let's jump into it. An ionic bond is the bond between two atoms, which is the electrostatic force which holds together the ions formed by the complete transfer of electrons from the electropositive to the electronegative atom. The definition may sound daunting, but don't worry, we'll break it down into little pieces for better understanding. The first thing is that it's formed between two atoms, and it is formed due to an electrostatic force. Right, let me just put a 2 there. Yep. So, how does this happen? Let's take an example. Potassium chloride. Now, the electronegativity of potassium is 0.82. 0.82 and chlorine is 3.16. Therefore, there is a high electronegativity difference. I'm just going to write it as ED between them, which is equal to 2.34. So here we come to the first condition for the formation of an ionic compound. It must be formed between a metal and a non-metal with a high electronegativity difference. So I'm just going to put that down here in a different color. High ED, electronegativity difference. Then, because of this high electronegativity difference, potassium, which has one electron in its outermost shell, decides to donate, completely give away its electron to chlorine, which has 7 electrons in its outermost shell. So chlorine has now 8 electrons in its outermost shell, but potassium has 8 electrons in its outermost shell as well, because potassium's original configuration was 2, 8, 1, and when it lost that one electron, the penultimate shell became the outermost shell, which means that the configuration of potassium now becomes 288. So, to recap, the new configuration of potassium 288, but the number of protons in potassium doesn't change and it's still equal to 90, while the number of electrons has decreased by 1 and is now equal to 18. If you add 288 and C, it's equal to 18. So there is a net unit 1 positive charge on the potassium, while since chlorine accepted 1 electron to get a stable octet, there's a net negative charge of -1 on chlorine. So potassium is called electropositive. I'm going to write that as EP, and chlorine will be called electronegative. I'm going to write that as EN. So we know that a positive and a negative charge will attract. So K with its +1 charge is attracted to Cl with its -1 charge by something which we call the electrostatic force. So this would work for any ionic compound. Basically, this is how ionic compounds are formed. Okay, so a covalent bond is the attractive force which comes into existence between two atoms due to the mutual sharing of electrons between atoms of same electronegativities or a small difference of electronegativities. So, what does this mean? I will tell you through a story, the story of water, or as we like to call it, dihydrogen oxide. So, once there was a lonely oxygen. Let me just draw this lonely oxygen atom right here. It didn't want to form any ionic compounds. There was another lonely hydrogen, two of them in fact. They didn't want to form any ionic compounds either. Now, hydrogen, both of them had only one electron in its outermost shell. It didn't want to form any ionic compounds, but it did want to give its electron away in donation so that it could attain stability. And oxygen, on the other hand, it didn't want to form any ionic compounds either. So basically, it wanted to take two electrons. It had six already. It was just so close. It wanted to take two electrons so that it could achieve stability. So these two hydrogens and oxygens come to an alliance. What do? Let's see. So these two hydrogens and oxygens decide that sharing is caring. Sharing is a better way in which all of them can achieve stability without having to transfer any electrons. So they have their own electrons with them and they're stable. It's a wonderful arrangement. Let's see how that happens through the Lewis structure of water. So I'm going to go ahead and draw the six electrons of the outermost shell of oxygen right here. That's 6 for you. And one dot for hydrogen right there. So they share their electrons like this. Pardon my circles. Like this. So as we can see, it looks a little bit like a set. These two electrons and these two electrons are being shared. Oxygen contributes one electron to be shared, while the hydrogens, well, they contribute one because they only have one to share. And as a result, if we count, hydrogen has a total of 2 electrons in its outermost shell. This hydrogen has a total of 2 electrons in its outermost shell. So the two hydrogens are stable. And if you count the oxygens, they have a total of 8 electrons in the outermost shell. So the oxygen is also stable. And they all win. So how do we represent this? We represent this as dihydrogen oxide. There you go. Let's take another example. This time we'll take a diatomic molecule, nitrogen. So here you have one nitrogen. Since its valency is -3, it has 5 electrons in its outermost shell. I'm just going to go ahead and draw them here. And even though it's the same atom, I'm going to represent it in another color. I'm going to go ahead and draw that here. So this is basically its Lewis structure, how it shares the electrons between themselves. Here you go. So we see that 1, 2, 3 pairs of electrons are shared, or in total 6 electrons are shared. Now the electrons that are not shared, that are left behind with the original atom, are known as lone pairs. We can see 1 lone pairs or 2 lonely electrons in each nitrogen atom. So if we count them all, we'll see that each nitrogen atom has 8 electrons and hence it's stable octet. We can represent that like this. Nitrogen triple bond, another nitrogen. So basically, this is the principle of covalent bonding. Now, as I leave you to understand covalent bonding better, let me leave you with this thought. Suppose you and your friend both have 5 pencils each. Now, for some strange reason, you need 8 pencils, and there is no possible way you're getting 3 pencils last minute. So, what do you and your friend decide to do? You decide to share your pencils. So, let me put your pencils down like this in green. There's your 5 pencils and your friend's pencils in purple. Right. So, both of you have 5 pencils. You need 8 pencils. What do you decide to do? Share, obviously. You're thick as thieves. So, you share 3 pencils. You share these 2 pencils. You share these 2 pencils. And you share these 2 pencils between each other. As a result, let me represent you in light green here. You have 1, 2, 3, 4, 5, 6, 7, 8 pencils. Just the number you require. And how many pencils does your friend have? Oh, let me just get that out of there. Yes, your friend has 1, 2, 3, 4, 5, 6, 7, 8 pencils. Bingo! Both of you have 8 pencils each, and you didn't even need to get new ones. Now, let me show you a similar example for ionic bonding. So, let's say your friend has 1 pencil, 2, 3, 4, 5, 6, 7 pencils with her, and you have 1 pencil with you. So, your friend, she needs 8 pencils for her upcoming test, and you don't really have a test right now. So, you're okay with giving her the only pencil you have so that she gets good marks on her test. So, that's 1, 2, 3, 4, 5, 6, 7, 8 pencils for your friend and 0 pencils for you. That is the concept of ionic bonding. So I hope you understood this video, and please subscribe to my channel and like my video. This is my first video. So please subscribe to my channel if you want to see more. Thank you.